Last lecture, we learned about the adder. We talked about mirror adder, right? So now you are ready to do your project. In particular, we say that we have this ripple carry, which is very slow. The carry will propagate from one bit to another, right? So how is it related to number of bits in terms of the delay time? Can someone tell me? If I have n bits, what will be the delay time? So this is like in computer engineering, right? We talk about order. What is the O, the big O, right? Is O of what, right? That is the, for example, O of n. It means that the order of n, it means you have 10 bits, you may have this amount of delay. 100 bits, it will be 10 times longer, right? So how is the delay of a ripple carry depends on the number of bits. Anyone want to tell us? No? It is proportional to n, right? Correct? If you have more bits, then you take longer time to propagate. Is that clear? Any question? Now, then we talk about, we say that, well, we can also, the reason that is so slow is because of the carry. Can we bypass the carry? That's why we have so-called back carry bypass adder, right? So what we do is that we have this multiplexer. Do you remember what is the input of the multiplexer to select whether it is the carry from this block or the carry that bypass? Even you don't remember the exact answer, does it ring the bells for some of the any quantity that might be related? Generation, yeah, propagation, yeah.
All propagations should be 1 for it to select.
Thank you very much. Right, we need P0, P1, P2, P3, right? Bypass, right? If they are all 1, then you will just take this one because this is a multiplexer, right? You will take this one. Otherwise, you will take the top, right? So when we start the running, we don't need to propagate through this block anymore, right? We will just propagate direct through this bypass, right? So here we have the setup time, and then we need to propagate within here, which has m bits, so m t carry. But after that, you only need to propagate n divided by m multiplexer, okay? And actually, I think this one should be -1.
Professor,
yes.
Professor, small question.
Yeah.
Actually, I wanted to know, like, when we are having all propagations as 1, that is like only one state, right? Out of so many states, that will be only one state.
Yes, yeah, only one state, only this state, all 1. Yeah.
Like, is it worth like we are using more number of transistors, which consumes more area and power? Like, is it worth it to have for that just one state to use the propagation?
No, you not save one state, you save many stages. You only need these 2, the first and the last stages, to still have this carry propagation. But in between, you just propagate directly through this multiplexer. You don't need to go through this carry propagation.
Oh, okay, okay, I got it.
Yeah, so think about if I have many in between, then you save a lot. Even here is safe also. Okay, yeah. Yes. So here n divided by, I look at the wrong thing, right? -1, that is correct here. N divided by n, the bypass. Okay, and then at the end, you need to do the carry again, right? I don't know if you really understand, but this always confused me, and I even maybe say something wrong last time. But basically, you might say that, hey, what if the output depends on this one, right? Then how can I just copy from here, right? If actually this carry, I need to, all this propagation is not 1, then I need to select this one. If you select this one, you basically say what? It means this guy will generate. So it does not depend on the previous carry. If this one will generate, then since this one and this one run at the same time, right? So your delay is only from here to here, right? So this is the worst case already. Okay, so this is carry bypass, and you see clearly now the delay is empty carry, actually 2 empty carry, right? Compared to n can be 128 bits, but here m can be just 4, so it is much faster. But you are still not happy, right? As an engineer, right? As like all of us, the whole history is about really greedy, right? Because we're greedy, that's why the engineering is so important. We want to even save more. We say that, can I just skip this carry propagation? So we come up with something called linear carry select. The carry select is what? We only have empty carry. We don't have this last term. So why? Because we say, let me just prepare everything. Even I don't know what carry it is, let me just calculate it as 0 and 1. Assume I have 0 input, carry in, then I already calculate the correct result. Assume it is 1, I calculate the correct one. Then you just wait until this one come in, I select the right one. So same for every stages. So in here, you will just carry already calculated, even the carry is not here. Once the carry reach here, you just select the right one and then output. Okay, so this is called linear carry select, but not this figure. Why? Because this figure you have 2, 3, 4, 5 bits, right? This is actually square root carry adder. It is even better because we know that this one, if in linear carry select, if you have the same number of bits, it's going to wait for it to propagate because I have a multiplexer to extra path for this one to propagate, right? So we make this longer, and as a result, we can get square root n of the T-max delay. In terms of carry, it's still empty carry. Okay, any questions? Right, so I don't worry about this much because you are the one going to do the schematic, do the layouts, and do everything, right? So I think the topic you learn the best in this class will be this adder because you are going to do it in the project. Okay. Now let's continue. I talk about the carry look ahead. This is just a repeat of what we said. We say that we are even greedier, right? We say that I even don't want to have any delay in calculating the carry. Why do I need to wait for propagation if carry is so important? Let me just calculate it on the spot. It means that I need to take all the A and B and calculate the carry, right? And the way we design the circuit is more logical and more intuitive and turn out to be more efficient. It's just to think the carry as carry out is either I generate or I have a carry in and then I propagate. This is a very logical way of thinking, right? Okay. I'm rich, either I generate a lot of money or let's say, maybe it's better. Let's say I can give a lot of money to my kid. Either I generate a lot of money, then have money to them, right? Or my parents give me a lot of money and I propagate it to my kid, right? So this is very reasonable. And then you just keep expanding. Eventually you have this. And basically this, again, is also can explain verbally. Bit 3 has carried out if the last bit generates or ... input has carried in and then 0 bit 1, 2, 3, they all propagate, right? And just my grandfather's grandfather is rich, and then my great-grandfather propagates, my grandfather propagates, my father propagates, I propagate, then yeah, my son will be rich, something like that, right? So by doing this, then we get this, but we say you need to be very careful when we lay out this because you are going to have n plus 1 branches, and that is going to increase the drain with capacitance. And I hope you still remember what is the meaning of drain capacitance is related to the P, right? The P value. right? If you size it so that it has the same resistance as a inverter, your drain capacitance is very large because you have n+1 transistor connected to the output, right? And similarly, you have n+1 transistor stacked, and that is very resistive. Remember the Elmos delay? It basically tells that I have n square more delay. So you cannot say I have 128 bit of adder. I just put all this 128 times 2 signal and then have a big logic function to find out what is the carry out. That is not going to work because it's going to be very slow. 128 square is talking about more than 10,000, right? Any questions? But this is okay. We can do something. Again, as an engineer, we always can find a way. But before that, we introduce this notation, right? We say that, hey, let's don't just look at a bit as carry and generate. We can look at the group of bit as carry and generate. For example, bit 0 and bit 1 can be looked as a group. If you go through the map, again, it's very logical. It's saying that I have the bit 0 and 1 group, right, has a carry out if the whole group from bit 1 to bit 0 generate, or there is an input, right? Here is basically talking about C in 0. There is a carry in, and then the whole group propagate. But what do you mean by whole group propagate? Of course, it again means that bit 1 propagates and bit 2 propagates, right? Think about this. Okay, and what do you mean by the whole group generates? Of course, either bit 1 generates or bit 0 generates and then bit 1 propagates. And that is exactly what it is talking about here. Okay, by doing this, then we'll be able to concatenate different bits. For example, I have 2 bits, right? Like here's 3, bit 3, and then bit 2. I just concatenate them. The whole group will becomes what? Will becomes generate for 3-2 and propagate for 3-2, which basically is saying that, which is this dot product. Okay, the generate again is 2 generate, 3 propagate, or 3 generate. Propagate is 2 propagate and 3 propagate. These are just the notation that can help us to understand more. Is this okay? Right, but why do we want to do this? Because it helps you to simplify your logic and understand your logic. So last time we stopped here. So what we want to do, for example, right? For example, if I look at this one, S7, I want to ask, is the output 7? How do I do the logic for output, for the carry out of 7? Then it is very easy. It is just saying that, let's just think it as a whole block, or maybe from 0 to, I think I should put 7 to 0, generate, or 7 to 0 propagates, but the input, but we have a carry in, right? This is very easy. This one is okay, right? But instead of keep doing this thing, we are going to use so-called logarithmic carry on. Look ahead, we will decompose them, right? So here we will ask ourselves, what is G70? Okay, now if you look at here, right, this is still G70, right? G70 equals to what? Equal to either, we look it as, we keep partition it into half, right? So this becomes G7 to 4. Either G7 to 4 generate, or P7 to 4 propagate. Okay, right? And the same thing is, and then we continue, right? You have G7 to 4. Then how about, now we need to ask about G7 to 4. How is it depends on others? we keep dividing into two parts. Then we say, okay, this is G7 to, sorry, actually I did the wrong thing because we're talking about 7 to 4, it should be this branch, right? G7 to 6 generate, or G5, G7 to 6 propagate, right? So now you see that I actually make a mistake. When I say G7 to 0, right? I'm talking about this block, right? It is 7 to 4. Here is 7 to 4. So what should be the input? Should it be C in 0? This is not C in 0, right? This should be the carry in from the previous spot, which is the generate of 3 to 0, right? So I make this mistake, right? So you're saying that, okay, 7 to 4, the whole thing, 7 to 0, this whole thing generate is either 7 to 4 generate or 3 to 0 generate and then 7 to 4 propagate. That's what it's trying to say. Okay. And similarly, this one will be G5 to 4. So what does it say? 7 to 4, this whole group generate either 7 to 6 generate or 5 to 4 generate, but 7 to 4 propagate, right? So you keep break down the tree and the number of hierarchy will be logarithmic, right? Because you keep divide it by 2. And this will be something easier to implement. So that's all I want to talk about the logarithmic lookahead. Any questions regarding this? Okay, if no, let's move